Hello everyone, this is Rohan Mishra and welcome to my lecture series on bioinformatics. And today we would be starting out with a new topic called as multiple sequence alignment. So far so good. In our previous videos and lectures I have discussed on how do we align two sequences with, and we have discussed technique like pairwise sequence alignment. We have discussed what are different ways in which we can align two sequences, that is global alignment, local alignment, and what are different algorithms that are implemented in aligning two sequences globally and the two sequences locally as such. Well, now let us stretch our discussion to include more than two sequences. What if we have the situation that we might want to compare more than two sequences, 3, 4, 5, and multiple sequences as such. Okay, so such a kind of problem is usually addressed using something called as the multiple sequence alignment, or MSA, of the given sequences. Okay, so theoretically it is possible to extend the concept of dynamic programming to include more than two sequences in your alignment. But if we stick on to the concept of dynamic programming and stretch that concept to include multiple sequences in your alignment, although theoretically it is possible, but practically it would take a lot of time as well as computational resources to do so. Therefore we need to develop, or we need to devise a new strategy that will be more optimized for aligning multiple sequences, rather than simply relying on whatever we have learned in our previous lectures like dynamic programming. Okay, so it is said that multiple sequence alignment is usually conducted using a procedure called as progressive strategy. Okay, so most common and most popular multiple sequence alignment algorithm are based on these progressive strategies. We say that these multiple sequence alignment algorithm follow the progressive strategies to align those sequences. Okay, so now well, let us talk a little bit about this progressive strategy. Right. So the general strategy for aligning multiple sequences, well, the progressive strategies that we are talking about. In such progressive strategies, what we do is that we start out with a pair of sequence. Okay, that is, we select a pair of a sequence and align the two sequences as such. Okay, and then subsequently each of the remaining sequences are aligned to the previous alignment. Okay, well, say for example, if we have been provided with a task of aligning these 5 sequences, as I am showing over here, sequence A, sequence B, C, D, and E. Suppose that we are supposed to align these 5 sequences. So in progressive strategy, what do? Somehow we select an initial pair of sequences and we align them. Suppose we have selected A and B as an initial pair and we kind of align them, and once we align A and B, then we go on progressively adding the remaining sequences to our alignment like this. Okay, and since we are progressively adding one sequence after another, we say such strategy as a progressive alignment strategy. Okay, so now such progressive alignments are example of a heuristic algorithm. Okay, and more precisely we would call such algorithm as greedy algorithm. What is heuristic? Heuristic is nothing but approach to find a solution by trial and error. Okay, so well, say for example over here, heuristics we can apply, like we would try to find out a solution to the given problem of aligning multiple sequence by doing some trial and error, right? So well, first we would try out aligning A and B, then maybe we can try out first aligning C and D, or D and E, and then see how things work. Okay, so if you are trying to find out a solution to any given problem by trying out different thing, we say that the approach that you are using is heuristic approach. Okay, and greedy algorithm are part of such a heuristic approach, in which these greedy algorithms specifically decompose the problem into small individual pieces. And once you decompose the bigger problem into smaller pieces, what you try to do is you try to generate the best solution to each small piece without paying attention to the problem as a whole. Okay, so by that what I mean is that our main problem over here is to align these 5 sequences. Now how do this greedy algorithm work is that we would divide our bigger problem into series of shorter problem. We'll say, for example, how do we align A and B? How do we align B or C? How do we align C or D? C and D. How do we align D and E? How do we align A and C? So on and so forth. What we will do is that we would decompose the multiple sequence alignment problem into a series of pairwise alignment problem as such. Okay, and when we try to find out solution of as to how do we align sequence A and B, we won't pay attention on how alignment of A and B would affect the bigger problem of aligning these multiple sequences at the same time. Okay, so what our objective is in greedy algorithm is to find out the best solution for a given smaller problem without considering how it would affect the multiple sequence alignment or the bigger problem as such. Such a type of algorithm are called as greedy algorithm, and that is how most of the progressive strategies work on. Right? Good. So, in case of, that is what we have discussed, in case of MSA, the overall problem of alignment of many sequences is decomposed into a series of pairwise alignment steps. Okay, so now since these progressive strategies are heuristic in nature, and heuristic algorithm, don't guarantee to find out the best possible alignment, or what we call it as the optimal alignment. They would offer you with multiple solutions, and it would be completely dependent on you on what solution do you prefer. Okay, so progressive alignment don't guarantee to find the best possible alignment. Okay, so now there are many progressive alignment strategies that are available, and such methods differs in several ways. Well, say for example, any two progressive alignment program might differ in the way these programs choose the initial pair of sequence. Well, say for example, if you have got these 5 sequence, let us continue our example, previous example, A, B, C, D, and E. Okay, well, say for example, if you want to compare these these 5 sequences, and well, say for example, we have progressive alignment program X and progressive alignment program Y. These are two programs. Okay, and how these programs can differ? This X program can have some different rule for selecting what might be the initial pair. Okay, while this Y program, which is again progressive alignment program, it might have some different set of rule for selecting the initial pair of sequences. Okay, so in this way, different progressive strategies implementing program might have different rules for selecting the initial pair. Okay, so it is entirely possible that the programs aligns every subsequent sequence to a single alignment, and right? So it is possible that this X, one of the progressive strategy program, it might align every subsequent sequence in the set of given sequences to the previously aligned sequences. Okay, or it is entirely possible that this program Y can create a subfamilies. Well, say for example, what if I align this A to B and then I would align C, then I would separately align D and E, and after everything has been done, then I would combine all of my alignments. Okay, so that is what it means, that some program can create subfamilies like this. Well, it was in one subfamily, this ABC were in another subfamily, and then families can be aligned with each other. Or the other way around is, first we would align A and B, then we would subsequently add C to the previous alignment, then would we add progressively add D to the previous alignment, and then we add progressively E to the previous alignment. So in this way the programs can differ, either they can subsequently add one sequence after the another to your alignment, or they can create subfamilies of the given sequences and then align those families. Okay, so this is how these programs that are based on progressive strategies can differ. Okay, programs from progressive strategies can also differ from each other in a way they score individual alignment. Okay, or the way they score alignments of individual sequence to the previous alignment that has been already generated, right? So scoring can be a criteria in which two alignment program can differ. Two alignment program can differ in the way they select the initial pair, or the progressive strategies program can differ on the basis as to how they align the sequences, whether they create subfamilies or they subsequently go on adding progressively the remaining sequences that are left in your set. Okay, so these are the different ways in which such progressive alignment methods differ from one another. Okay, so there are many programs in progressive strategies. Well, say for example, ClustalW, there is example Muscle, Tea Coffee, and so on and so forth. These are different programs that are somehow based on progressive strategies, and they can differ in these three ways that we have discussed so far. Okay, so now we won't go into more details of other programs like Muscle or Tea Coffee. We would focus only on the simplest one, that is Cluster. In our further course of discussion, we would take an example of ClustalW as one of the model progressive alignment computer program. Okay, so let us discuss this ClustalW. What are the steps that are involved in your ClustalW? What are what are the strategies that are used in aligning the multiple sequences using ClustalW? That would be the major focus of discussion of our today's lecture. Okay, so to briefly begin, there are 5 steps that are involved in aligning the multiple sequences if you are using ClustalW. So there are variants of this Clustal. You can have Clustal X, you can have ClustalW, you can have Clustal Omega, Clustal X2, so on and so forth. Okay, this W stand for weighted. Okay, so we are going to learn the typical algorithm of Clustal called as ClustalW. Right. So as I have already mentioned, there are 5 steps that are involved in aligning multiple sequences by using ClustalW. The first step would be creation of pairwise distance matrix for all of the sequences that are needed to be aligned. So once you create this pairwise distance matrix, you are supposed to generate something called as the guide tree. And this guide tree is supposed to be generated using a technique called as neighbor joining algorithm. Once you end up with a guide tree, and well, say for example, you have got these multiple sequences. First, what you would do, you would create a guide tree out of these sequences. Okay, this is a guide tree. You have got sequence A, sequence B, C, D, and E. Okay, so first what would you do? You would convert this sequence information into, say, some numerical form by creating something called as the distance matrix. And using data from distance matrix, you would create a guide tree, and based on the data that you obtain in this guide tree, you would go on for the further process. Like, we'll say for example, in this guide tree, A and B appears to be most closely placed to each other. Okay, and in this way you would first align these sequence A and B. Okay, so based on the data on your guide tree, the alignment of most closely related pairs of sequences is done using the dynamic programming like Needleman and Wunsch. Okay, you would use Needleman and Wunsch to align these two sequences globally. Okay, then subsequently or progressively, these pairs are aligned to the remaining sequences that are left as per the order that is present in your guide tree. Okay, so in this way, when you add this C to the alignment of A and B, we say that you have generated a profile. Okay, so in this way, such profiles are aligned to each other or to other single sequences till the entire alignment has been done. Okay, so this is the brief account. Well, now let us talk into more details of how the distance matrix is converted and all those things. Okay, so the first step in your multiple sequence alignment procedure is to create a pairwise distance matrix for all of the sequences that are needed to be aligned. We'll say, for example, for the sake of simplicity, now we would consider that we need to align these four sequences. Okay, so the pairwise distance matrix is needed to be generated, which might look something like this. Okay, so why do we convert or why do we generate this pairwise distance matrix? This pairwise distance matrix is needed to be generated. Why? Because we need to convert the sequence information into numerical information so that we can compare these sequences. Okay, so in order to align the sequences, first we need to convert the sequence data into numerical data. Okay, and exactly that is done by creating such distance matrix. Okay, so the objective of creating pairwise distance matrix is to convert the sequence data, as you can see over here, into numeric data. Okay, so typically this distance matrix would show the distance between each pair of sequence in your alignment. Okay, for example, in this case, in our case, okay, the distance is expressed as the number of nucleotide differences per nucleotide site for each sequence pair. Okay, so for example, these sequence 1 and sequence 2 are 20 nucleotides in length. Okay, and since they are 20 nucleotide in length, what we have done over here is that now we know that this sequence 1 and 2, well, they have got difference at 4 position. Okay, these two sequences differ at 4 position. So what we have done is that we have simply divided the differences that are present by the number of residues or the number of characters that are present in these two sequences, and whatever number that you get, we can populate them in your distance matrix. So this 0.20 correspond to the distance between sequence 1 and sequence 2. Okay, so the idea is to obtain some numerical way by which you can decide which of the two sequences are similar and which of the two sequences are dissimilar. In this way, by by converting this data into distance matrix, what we are doing, our objective is to convert this sequence information into numerical information so that these numbers can further be used or further be manipulated in generating your multiple sequence alignment. Okay, so Next, what we do is that once we have obtained this data, the what we do is that we use the results from this distance matrix to create a guide tree. Okay, so guide tree would eventually help you to determine in what order the sequences are needed to be aligned. Okay, so such a guide tree or dendrogram will have no phylogenetic meaning. Okay, why? Because this guide tree is simply created based on the nucleotide or amino acid residue differences, and we haven't implemented any kind of evolutionary model in order to generate this tree. Okay, therefore such a guide tree or dendrogram has got no phylogenetic meaning. This is very important because I have seen a lot of students to infer that these two sequences are related to each other. Okay, so that is not supposed to be inferred. The objective of guide tree is to decide in what order these sequences are needed to be aligned. Okay, therefore this guide tree cannot be used to show evolutionary relationship, as they only correspond to how close or how distantly the two sequences are to each other. That is what it means. That is what this guide tree means, right? So, well, say for example, this is if this is the typical guide tree that you have obtained, and now based on this guide tree, you can see over here that in your guide tree, sequence A and B are very close to each other. Sequence E and F are very close to each other. Similarly, sequence I and J are very close to each other. Therefore, in this way, we can decide now that of the given sequence, based on the data whatever we get on this guide tree, we would first align sequence A and B. Simultaneously, we would align sequence E and F. Simultaneously, we would align sequence I and J. And based on what and how the remaining sequences are placed in the guide tree, we would go on subsequently adding the remaining sequences to our alignment. So this is the overall idea of how the sequences are selected and aligned. And in this way, this is something called as the progressive strategy to align the sequence. Why? Because we are progressively adding the remaining sequence to the previous alignment. Let's say for example, C would be added to the alignment of A and B, G would be aligned to the alignment of E and F, K would be aligned to the alignment of I and J. And since we are progressively adding these sequences, we say that this is a progressive strategy, right? So that is what we have discussed. The alignment of most closely related pairs of sequence in a guide tree is usually done using the dynamic programming. Okay, so we would be using dynamic programming algorithm like Needleman and Wunsch to align A and B globally. We would be using dynamic programming algorithm like Needleman and Wunsch to align E and F globally. Similarly, we would be using Needleman and Wunsch to align I and J globally as such. Okay, so we would be performing global alignment, right? So in our case, for our example, we would first align A, B, E, F, and I, J. Okay. Well, say for example, let us call the alignment of sequence A and A and B as alignment A. So it is entirely possible that you might end up align C and D, or some different alignment. Okay, we would call alignment of C and D as alignment B. What you can do is that now you can align these two alignments, alignment of alignment A and alignment B, to generate something called as profiles. Okay, so when you align two alignments, we say that you can generate profile, and we would name this profile as Q. So in this way, sequences are aligned, alignments are aligned to each other, or subsequent remaining sequences are aligned to either profile or alignments. In this way, you would generate the entire multiple sequence alignment. Okay, so if more than one profiles are present, then those are also aligned to each other. or we'll say for example if profiles can be aligned with new incoming sequences, and finally you would complete the multiple sequence alignment like this. Okay, so this is how progressively your multiple sequence alignments are generated, or progressively your multiple sequence alignment are built up. Okay, so now since you know, I hope that now you understand what is the basic idea behind generating such multiple sequence alignment using progressive strategies. Okay, and this is how your ClustalW works at least, right? So now let us talk about what are the factors that might affect the quality of multiple sequence alignment. Okay, so the first and foremost, the factor that would affect the quality of multiple sequence alignment is the scoring matrix. What type of scoring matrix do you use? Okay, how do you assign the penalties? How do you assign the gap opening penalty, and how do you assign or how do you handle the gap extension penalty? So gap penalties might also affect the quality of MSA. So when it comes to aligning profiles to each other and subsequent sequences to the remaining profiles, you would also consider something called as the weighing parameters in multiple sequence alignment. Okay, so what weighing parameters do you choose to select that would eventually affect the quality of multiple sequence alignment? Okay, so these weighing parameters are used in deciding the scoring metrics for sequence to profile alignment or profile to profile alignment. Okay, so what weighing parameters you use, how do you handle the gap penalties, and what scoring matrices you use, these three factors would eventually determine the quality of your multiple sequence alignment. So this is very important to know. Okay, so now let us talk some practical consideration of using ClustalW. Like when do you use ClustalW and when not to use ClustalW. Okay, so look, any computer program is based on say certain assumptions. So it is the duty of a biologist or a user of this computer program to know on what basis or to know on what assumptions any computer program is generated or built up. Okay, and you should know these things beforehand when you use such computer programs. Okay, so uh, this ClustalW is also based on certain assumption. Okay, so the first assumption that is that is understood that the user knows is that uh, when you use ClustalW, that means it is considered that whatever sequence that you would provide as an input to this program, those sequences are related to each other over their entire lengths. Okay, well, so for example, if you are using these three sequences and trying to align using multiple sequence alignment, trying to generate the multiple sequence alignment using progressive strategies, and if you are using ClustalW, that would mean that it is understood that this sequence A, B, and C are related to each other over their entire length. It is not like a short sequence from A and B is similar to this much sequence from C, okay, and the remaining sequence is not related. It should not happen that way. The entire sequences should be related to each other over their entire length. Okay, so this is the basic assumption that is assumed when you provide input to your cluster. Okay, so this ClustalW is optimized to align set of sequences that are entirely collinear. That means the sequence that have same protein domains in same order. Now you know proteins are modular entity. Well, say for example, if this is your sequence 1, well, say for example, it is having immunoglobulin domain over here. Then over the next span, you are having say some adapter domain like SH2, and then you might have say some another domain like it can be anything kinase domain. Okay, so Now when you give input to the programs like Clustal, then that is understood that all of the sequences that you are providing, it would contain the same Ig domain at first position, same sh2 domain at second position, and same kinase domain at the third position. Okay, and these domain appear in the same order in all of the given three sequences. That is what we say when we use the term like these are entirely collinear. Collinear है यानी क्या? The domains that are present in your sequence are in same order. It should not happen that in the first sequence you have got Ig domain followed by sh2 domain, and in third sequence there is sh2 domain first and you have got Ig domain at second position. The domain should not shuffle, right? Why? Because we are using dynamic programming and we would be aligning the two sequence globally. And when you try to align globally, then your alignment would be erroneous if the domains are interchanged or if the sequences are not collinear. So these are the two assumptions that are considered that the user knows before he provides the sequences to the softwares like ClustalW. Okay, so when not to use cluster. Okay, so it is advised that when the sequences do not share common ancestry, you are not supposed to use it in cluster. You need to have some background or brief idea about what kind of sequences you are dealing with. Okay, so do not use the sequences if they don't share the common ancestry, at least so far your cluster is concerned, right? If the sequences have large N and C terminal overhangs, you are not supposed to use them. It should not happen that the two sequences would differ significantly in the length as such. Okay, so they should not have the variable N or C terminal overhangs. If that is the case, don't use cluster. Okay, so if the sequences are partially related, you are not supposed to use cluster. Okay, only if the two or three sequences only they are related in these small regions over here like this, right? And the remaining sequences are not related, then you are not supposed to use such ClustalW. Okay, so if the sequences are partially related, that means only a small short such region like region Y is only similar in these three sequence and the remaining sequence is not similar or not related. In such a case, you are not supposed to use this cluster. Okay, if your sequence includes short non-overlapping fragments, then also these are not good candidates that can be used for aligning it using the ClustalW. Okay, so simple fact, if you provide garbage in, the program will give you garbage out. Okay, so the quality of your results would be completely dependent on what kind of input do you give to your sequence to your computer program. Okay, it is your responsibility to provide a quality data and expect the quality output from it. Okay, that is it. Now let us discuss what are problems with cluster. Okay, so does the quality of guide tree matter? Okay, the guide tree that we have discussed. One might ask this question, will the quality of the guide tree somehow affect the quality of my multiple sequence alignment? Well, most of the time, if the sequences are closely related to each other, the quality of guide tree won't make much of the difference. But if the sequence are very distantly related and they are very divergent, then of course the quality of guide tree might affect the quality of your multiple sequence alignment. Okay, Now the biggest problem that this cluster face is in form of this single parameter problem. Okay, so say for example, uh, if you are using one weight matrix and one set of penalties for all the sequences, then it might become problematic. Why? Because the best set of parameter for one part of the alignment may not be the best part for the another. Okay. Moreover, in your protein sequence alignment, different scoring matrices are to be used for each alignment based on what is the expected evolutionary distance between the two sequences that you are dealing with. Just to give you or to explain you in simpler word, well, say for example, let me draw the sequences first. Draw or give you an example. Okay. Well, say for example, if you end up aligning these 5 sequences, okay, so and what do you do when you align the sequences using progressive strategy? You would generate a distance matrix, okay, and based on the data from distance matrix you would create a guide tree. Okay, say for example we have 6 sequences. Okay, so what we mean is that if you are trying to align the two sequences that are close neighbor in your guide tree, let's say for example sequence 1 and 2 are very close neighbor in your guide tree, right? So what you are supposed to do is that you are supposed to select a scoring matrix that is optimized for close relationship to align them. Okay, on the other hand, if you are trying to align the sequences that are distantly related to each other, or you can say that 4 and 5 are distant neighbors, and you are when you are trying to align these two sequences, you are supposed to use the scoring matrix that is optimized for aligning the two sequences that are distantly related to each other. So we have different set of scoring matrices to do this job. Well, so for example, you can use this Blossom 62 to align the sequence 1 and 2. Why? Because they are found to be closely related. Okay. On the other hand, you can use Blossom 45. Why? Because you know that these two sequences are divergent, and these are distant neighbors in your phylogenetic in your uh, guide tree as such. Okay, so the thing is that the problem is what we call it as the single parameter problem. If you use the same scoring matrix to align the two sequences, or the two set of sequences that are somehow distantly related, or that are differentially related to each other, then it might become problem. Okay, so the scoring matrix are to be appropriately used. Okay, so that is what is said in the sequence alignment. Different scoring matrices are used for each alignment based on what is the expected evolutionary distance between the sequences. The expected evolutionary distance between the sequence 1 and 2 is small. Okay, or you can say they are closely related to each other as compared to 4 and 5. Therefore, different scoring matrices are to be used to align these sequences. You cannot use the same scoring matrix to align all the sequences as such. Okay, so this is included in the single parameter problem, right? Next, what we have is called as the local minimum problem. Okay, so if it happens that alignment goes wrong in the initial stages of your multiple sequence alignment, then that problem cannot somehow be removed in the subsequent step. that problem would be carried out as it is in your multiple sequence alignment, or even it can be amplified. Okay, so that is what it is termed as local minimum problem. If the initial alignment have problem, if the initial alignment have some error, it cannot be removed in subsequent step. Okay, that is what we call it as the local minimum problem. If you go wrong while aligning the sequence 1 and 2, then such a mistake cannot be rectified later. In fact, the mistake can be, amplified when you go on progressively adding the remaining sequences as such. Okay, now let us discuss another aspect of your evolutionary analysis. Some people might ask, okay sir, what is needed to be considered when you perform evolutionary analysis? Shall I use the DNA sequence of my gene, or shall I use the protein sequence of my gene? Okay, so one can put forth an argument like DNA can show underlying mutations that will not somehow appear in your proteins. Okay, you have got Wubble based mutation that would seldom change the protein sequence. Let's say, for example, your glycine can be coded by multiple codons. GAA would code for glycine, GGC would code for glycine, so on and so forth. Okay, so in this way, many phylogenetic program ignore the third base, right? Considering that there is sense of wobbleness in the codons as such, right? And to this, someone can also put forth a counter agreement saying that whatever mutations that happened in such a way, these are very silent mutation and they don't reflect the true rate of evolution. Why? Because they are not under evolutionary pressure. Okay, so in contrast, if you consider amino acid mutation, well, these amino acid mutation reflect the true rate of evolution as they are under evolutionary pressure. If the amino acid residue changes, that would eventually change the function of your protein, and if the function of the protein is changed, it can be either selected or that mutation can either be discarded in the selective pressure or in selection procedure, right? So these are the ways one can argue if or not to include what are the pros and cons of using DNA or protein in your evolutionary analysis. Okay, so there is also another observation that DNA may change, but whatever protein that it codes, that can remain the same. We'll say, for example, over here there are two DNA sequences shown over here, but they code for a single protein, or the protein with the single sequence, right? That would eventually mean the protein could be under evolutionary pressure. So if you only use the protein data, you won't see all of the mutational events that are going to happen in the background. Okay, so now to consider protein sequence or nucleotide sequence in your evolutionary analysis is usually context dependent. It depends on what is the objective that is set by the researcher, right? So it is advised that you use the nucleotide sequence when the objective is to find out as to how mutation affect the evolution of genes or genomes or protein sequences. On the other hand, if your objective is to find out how these mutation affect the functionality of protein over time, then you are supposed to select the protein sequences in your evolutionary analysis or phylogenetic analysis. So I hope I have answered the question as to when to select what kind of sequences as such. Okay, so let us stop over here. Okay, and we would begin our discussion with phylogenetic analysis in our next or subsequent lecture, right? So this is all I have for you guys today. Thank you very much for your kind attention.